Acceleration of a body rolling down an inclined plane. Okay. Let a body of radius small r. Let a body of radius small r, mass m, roll without slipping down a smooth inclined plane having an angle of inclination theta. Angle of inclination theta. Suppose small v is the velocity of acquired by the body after traversing of a distance, s along the plane. Let omega be the angular velocity about an axis. Let omega be the angular velocity about an axis through the center of the body. Now, in one revolution, the body moves a distance 2 pi r, whereas point on the ring turns through 2 pi radius in the same time. Okay? Now, in one revolution, the body moves a distance, the body moves a distance, the body moves a distance 2 pi r, where is a point on the ring, turns through 2 pi radians in the same time. Okay? Linear velocity small v equal to r omega equal to small v by r. Okay? If I is the moment of inertia and small k is the radius of gyration of the body about the axis of rotation, then total kinetic energy of the body consists of first one, energy of translation. Energy of translation is 1 upon 2 mv square and second. Energy of rotation is 1 upon 2 I omega square, that is 1 upon 2 mk square omega square. Okay? Total energy equal to 1 upon 2 mv square plus 1 upon 2 mk square omega square. In moving a distance s from A to B, S, and moving on S from A to B, moving a distance S from A to B, the body comes down vertically, or distance AC equal to S sin theta, or distance AC equal to S sin theta. Okay? S equal to S sin theta. Hence the change in potential energy. Potential energy equal to mgs sin theta. Okay? since there is no slipping, no energy is dissipated, and the total gain in kinetic energy is equal to the change in potential energy. Equal to the change in potential energy. Since there is no slipping, no energy is dissipated, and the total gain in kinetic energy is equal to the change in potential energy, then mgs sin theta equal to 1 upon 2 mv square plus 1 upon 2 capital mk square omega square, that is 1 upon 2 mv square plus 1 upon 2 mk square v square upon r square, that is 1 upon 2 mv square 1 plus k square upon r square. Okay? Then as g sin theta equal to v square upon 2 1 plus k square upon r square. Differentiating with respect to time t, we get ds by dt g sin theta equal to 2v upon 2v upon 2 dv by dt 1 plus k square upon r square, that is v dv by dt 1 plus k square upon r square. Okay, now ds upon dt is linear velocity v, and dv by dt is acceleration, that is dv by dt v 1 plus k square upon r square equal to vg sin theta, this is vg sin theta r dv upon dt equal to a equal to g sin theta whole upon 1 plus k square upon r square, 1 plus k square upon r square. Okay, this shows that for a given angle of inclination of the plane theta, the acceleration is inversely proportional to 1 plus k square upon r square. This shows that for a given angle of inclination of the plane theta, the acceleration is inversely proportional to 1 plus k square upon r square. Thus 1 plus k square upon r square. Thus, first point, greater the value of k as compared to r, the smaller is the acceleration. Smaller is the acceleration of the body moving down an inclination plane, and hence greater is the time taken in rolling down the plane, and hence greater is the time taken in rolling down the plane. Second point, The acceleration is independent of the mass of the body. The acceleration is independent of independent of the mass of the body, mass of the body, independent of the mass of the body. Okay. Special cases. Next is special cases. 1 minute. Special cases. Special cases. Special cases. First is cylinder. First is cylinder. First is cylinder. The moment of inertia of a cylinder the moment of inertia of a cylinder, the moment of inertia of a cylinder about its axis of symmetry, about the moment of inertia of a cylinder about its axis of symmetry, about which it rolls, about which it rolls, is 1/2 capital M R square. That is I equal to 1/2 capital M R square, and equal to mk square, or k square equal to r square upon 2, and k square upon r square equal to 1/2. Okay. Hence A equal to G sin theta upon 1 plus k square upon r square, that is G sin theta upon 1 plus 1/2, that is 2/3 G sin theta. Okay. Second point, solid sphere. The moment of inertia of a solid sphere about a diameter about which it rolls is 2/5 mr square. If I equal to 2/5 mr square, that is mk square, or k square equal to 2/5 r square, and k square 1/r square equal to 2/5. Hence A equal to G sin theta upon 1 plus k square upon r square equal to G sin theta upon 1 plus 2/5, that is 5/7 G sin theta. Has solid sphere. Okay. Second, third, hollow sphere. The moment of inertia of hollow sphere about a diameter about which it rolls is 2/3 mr square, and I equal to 2/3 mr square, that is mk square, or k square equal to 2/3 r square, and k square upon r square equal to 2 upon 3. Hence a equal to g sin theta whole upon 1 plus k square upon r square, that is g sin theta whole upon 1 plus 2 upon 3, that is 3 upon 5 g sin theta. 3 upon 5 g sin theta as an example for, okay, 3 upon 5 g sin theta. Okay. Next is products of moment of inertia. Products of moment of inertia.